Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment.
This experiment, which enables one to measure the force between two charged plates, and thus the epsilon naught of Coulomb's law, involves a balance which is arranged slightly differently from other balances in that it has a stop on it, and two plates, one of which is grounded, the upper one, and a lower one which can be supplied with a high potential ranging up to 4 or 5 kilovolts. The space between them can be varied, and the potential can be varied. Before using the experiment, one has to make several adjustments, and these involve centering the part of this upper grounded plate on which the force is measured. Let's look down on the top of that for a moment, and we can see how it's constructed. There's an outer part here which is grounded and at the same potential as this inner part, but the outer part acts as a guard ring, and any edge effects which were due to non-uniform fields near the edges are therefore eliminated by having a smooth potential difference. On the other, however, in order to use the balance, this ring must be well centered in there. That's done in two ways. First, this plate can be moved sideways just a little bit to give the ring a uniform, this space, a uniform distribution on both sides. And finally, the leveling screw on the balance can be used to make the space uniform in both directions like that. One wants to be sure that this wire that you can see here connecting the ground of the balance to the ring is connected, otherwise that'll be floating and one will get unreliable, electrically floating, and one will get unreliable results. In addition to that, one will have to make an adjustment to make sure that the plane of this ring is exactly the same as the plane of the guard ring. That's done by taking this out and sighting along the undersurface of the grounded plate. There are adjusting screws here which can be used to make this plate parallel. Notice that when those adjusting screws are in the wrong place, as they are now, you can see the edge of it must be up against the stop. You can see the edge of this circle by sighting underneath there. So one wants to adjust these screws until that, no matter which way you look in, it's clear that the guard ring and the circle are exactly in the same plane. Again, make sure that it's in the center. And now one can adjust the spacing. The easiest way to use that is to use these little spacers. Each one is about 3 millimeters. Let's set it for about 6 millimeter spacing. One doesn't want to force that under there, or one will deflect that plate and undo the previous adjustment. So whenever one's moving these adjustment screws, leave the spacers out, try it. It's a little too loose. It's still a little too loose, and so on. Now just about right. So it neither fits snugly but doesn't deflect that plate. And then do the same procedure at all 4 plates and check the ones I've done. And then the balance is ready to use. So then one will want to do the balance. The reason for this stop is if, when the plates are charged, one allows this to go up, the 2 plates get closer and the force gets rapidly greater so that there would be no equilibrium position. So the best we can do is find out how much force on here it takes just to pull this away from the stop, that is to separate the plates. So we must balance it first, and that balance is achieved by finding the zero so that it just leaves the stop. That's obviously a little too much weight, and that's too little. It's hitting the stop, and about in here, it should just pull away. Let's look a little more closely. There, it just pulled away from the stop, and this is at a uniform balance. So this is my zero, and I'll have to write that down, and one should check it every once in a while, but there's no reason why it should change during the experiment. So now one's ready to charge up these plates to put a voltage between the two and therefore put some charge on them, and that's done with these power supplies. This measures the voltage. It's just an ordinary DC voltmeter with a high resistance and is calibrated, and the calibration is put on the front of it. This resistance, of course, this point is likely to be at 4 or 5 kilovolts, and therefore one doesn't want to touch either this resistor or any part of this lower plate here, whereas most of the balance is grounded. The power supply is this black box, which is a little oscillating power supply that's often used in TV circuits. It gives very high voltage, up to 5 kilovolts, or 4.5 kilovolts, but it won't, but it gives less than 1 milliamp, and therefore it will not kill you, but it can give you a very nasty shock. So try and stay away from it. This is in turn driven by this power supply, which puts out 250 volts and has a filament supply, and turns it from off to standby and lets it warm up. Make sure that this control is all the way down before starting up. The filament supply for here comes from these two wires, black and green, and the 250 volts comes from this here. So one wants to make sure that this meter switch is over on this side to measure that voltage. And one needs a separate ground for the filaments and for this side. The ground comes to one side of the meter and to the balance. Having done that, one then turns that to on and gradually raises this. If there was something wrong with the circuit, as this voltage comes up, this current comes up a rather small amount, because this doesn't take very much. If it should ever get beyond the red division, it would mean that something was wrong with the circuit and it should be turned off. However, as I turn it up now this voltage is coming up, and I'll set it at about 8, which on this calibration is about 4 kilovolts. And now you see that although that was balanced before, it hitting against the stop now. If I put this over here, it still just falls away now. Let me take this one, put it back now. It doesn't fall away. Of course, it'll stay down. That doesn't mean anything, but because when I do that, I pull the plates apart, and therefore the force is less. But what I want to know is when it's at the stop, is that just the right amount of weight? No. So there's probably fairly close. I can play with this till it just falls away, and also I can now, if I reduce the voltage a little bit, that force will decrease, and this weight will be enough to pull it away. So let me reduce the voltage just ever so slightly, and the balance falls away. So I want to get the value of this that I take will be that value, so that a slight decrease in the voltage makes the balance fall away. I'll put this back on standby. I can obviously do this for a variety of potential differences between the plates. I can change the spacing over a wide range, and then in addition, I can put various dielectrics in, dielectrics that are thinner than the space between there, and I can then, at the same potential difference, turn this on again, and notice that actually I've increased the force somewhat by putting the dielectric in, and by measuring accurately how much I've increased the force, I can determine what the dielectric constant is. So that this experiment now supplements the one on the force between two wires, where one measured mu0. Here one can accurately measure epsilon 0, because one has all the physical dimensions and the potential difference. And that's all there is to this part of the experiment.
Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television.